Hi, my name is Marcel, and today we're talking about a paper from Nicholas Carlini and David Wagner. These are researchers from UC Berkeley, and the paper is called Towards Evaluating the Robustness of Neural Networks. Let's dive right in. The main question we ask in this paper is how should we evaluate the effectiveness of defenses against adversarial attacks? So what are adversarial attacks? Let's see an example from a paper from Goodfellow et al. From 2015. Here we have an input X, which is an image of a panda, and then we add a carefully crafted perturbation, and in the end we will get an image that to us humans still looks exactly like a panda, but it is classified as a gibbon, and this even with a high confidence. So what happened? We found a perturbation of the input image by doing a gradient ascent on the input image. So we can see in the middle here we take the signs of the gradients, we multiply these by a really small constant. 0.007 actually corresponds to only changing the lowest bit of the encoding of the image. And by this we can fool the network by classifying the output as a gibbon. Alright, so what is a defense? The only thing that we have to change here, the output has to stay a panda. So if you train a network to be resistant against adversarial attacks, so to defend it against adversarial attacks, what you have to do, you have to find a way to make it robust against these attacks. So even after applying these perturbations, even after finding this modification of the input image, it still should be classified as a panda. So basically, adversarial defense means that we train networks that are robust against these attacks. So why do we care about this? Imagine you have a self-driving car, an autonomous vehicle, and then there's a stop sign. And this stop sign might have some perturbation in it. It could be a graffiti, it could be someone put some stickers on them, and then you have a problem because this stop sign here is actually classified as a 45 miles per hour sign. And you don't want to be in that car if this car just rushes past the stop sign without stopping. It can be really dangerous. This is one application. Another threat could be that you have spam emails that are not detected because the attacker added a couple of words that makes it seem benign. Or you can have computer virus that's not detected because it has been slightly modified in order to fool the virus detection algorithm. This example is actually from a paper from ACLR. It's called Robust Physical World Attacks on Deep Learning Visual Classification. So check out this paper if you want to know more about this example. There are also more harmless examples. For example, here we have a banana, and you can put this sticker on it, and suddenly it is classified as a toaster. This is pretty funny, but it shows us how easily these networks are fooled. So let's put this into historical context. In 2013, Segedi et al. They found out that there are adversarial examples in neural networks, and they found this for images. 2 years later, we had the paper from Goodfellow and his colleagues. That's the same paper that we talked about before when I gave the example of the panda. And he tried to explain why these adversarial examples happen. And his reason is that the neural networks are too linear, and they're too linear even despite us training them with nonlinear activation functions. But the reason for this is that we optimize over the steep parts of the activation functions where the gradients are non-zero. So in the end we end up with a rather linear network, even if it's not completely linear. A year later, Papernot et al. Developed a system called defensive distillation. This algorithm should make the network robust against adversarial attacks. However, it doesn't work against stronger attacks, which we will see in this paper where we evaluate the robustness of adversarial defenses. There have already been follow-up papers on robust optimization and more, so this is not the end of the road, it's rather only the beginning. So let's see what this paper actually does. When you want to evaluate defenses, you have two ways to do this. The two main ways are, first of all, to construct a lower bound on the robustness, meaning to have a guarantee that if the input is only perturbed that much, then the output will also be classified correctly. Basically, if you guarantee that the input is similar, then the output will be correct. When humans see a panda, the output should be a panda as well. Then second, that's what this paper talks about, is to demonstrate attacks to prove an upper bound on robustness. So we want to say this network is only that robust. We can break it at that point. And if you want to prove this, then you should use a strong attack, and then use this attack to show that the network is actually breakable. That's what we're going to do for defense distillation as well. Okay, so how would you train a network in order to be robust? There are several ways to do this. The most popular way is nowadays adversarial training. This means that you add adversarial examples to the training set, or you train only on adversarial examples, and the idea is that in that case the network learns to deal with adversarial examples and becomes robust by just training it on these examples. We're not talking about this in this talk, we're rather talking about defensive distillation, and we're going to see why it doesn't work. So if we want to understand how defensive distillation works, then we need to have a close look at the softmax function. The softmax function takes as input a vector x, and then it outputs a probability distribution over the logits. The logits are the values of the vector x. In this case, we modified the softmax function by adding a parameter t. T is the distillation temperature. So what we see here is that we scale the elements of x by dividing them by t. So let's think about what happens if we have a t that is larger than 1. Meaning that we divide the x's by a constant that is larger than 1, yielding x's that are smaller. So if you want, you can pause the video and have a thought about this. Okay, welcome back. What happens is if you use a t greater than 1, then the output of the softmax function will become more uniform. And if you use a really small t, let's say 0.1, then you will get an output that resembles more and more the max function. This is how it looks. Here we have on the x-axis, we have the logits, so the output of the neural network before applying the softmax function. And on the y-axis, we have the softmax. We can see in the middle for t equals 1, which is the standard softmax, that we have the S shape that we know very well. For t equals 3 already, we see how this curve gets less steep and goes towards a uniform distribution. Then on the left hand side we have t equals 0.1, and we see these really sharp edges, and this shows us that if t is small, we will get more extreme, a more extreme value for this function. And you can prove mathematically that as t approaches 0, we will get a max function, and if t approaches infinity, we will get a uniform distribution. Of course, this extends to more than just a two-dimensional cases here. Now we're ready to talk about defensive distillation. So how does it work? First, we train a teacher network, and this temperature should be greater than 1. What does it do? If the temperature is greater than 1, as we've just seen, the outputs of the softmax function become more uniformly distributed. And then we apply this teacher network on the training set, yielding new labels, and these labels are soft labels, so we will get probabilities like 0.6 for one class, and before, if we had trained the network with t equals 1, we might have got 0.9. So the outputs of these labels are closer to, in the two-dimensional case, to 0.5 than to 1. So they're more uniformly distributed than when we use a standard softmax activation function in the last layer. Okay, and this gives us a new training set with soft labels. And in this training set, we can train a distill network that has the same size, the same number of parameters, the same shape as the teacher network, but we train it on the soft labels. And again, we use a t greater than 1. And then when we test, we set t equals 1. So let's think about this. Can we break defensive distillation? We said before that the way to evaluate the robustness of networks is to find adversarial examples that break these defended networks. So let us find now an adversarial example for these distilled networks. For that, I would like to present to you the optimization problem on how to find adversarial instances. What we want to do, we want to find a perturbed image or a perturbed input x plus delta that is similar to the original input x. Delta here represents a perturbation that we apply. In the previous case, this was this image in the middle that consists of the signs of the gradient multiplied by a small constant. So what we want to find is this perturbation. But we have some constraints. We want to find a class T. In this case, T is the given. And we also have to make sure that the pixel values, x plus delta, are still in the range from 0 to 1. So this problem is pretty hard to optimize in this form, because C, x plus delta equals T is a highly nonlinear constraint. So what we are going to do now, we're going to reformulate this problem in order to make it solvable by a standard optimizer, let's say Atom. Because they actually used Atom in the paper. First thing we're going to do is to replace Cx plus delta equals T with an objective function f. And this objective function has to satisfy that Cx plus delta equals T if and only if the output of this objective function on the perturbed image, so x plus delta, is less or equal to 0. And second, we need to do something about this x plus delta in the range 0 to 1. And for that we can use the 10h function. And we do a change of variables. We replace x plus delta by this function on w. And you can convince yourselves that this yields a value between 0 and 1, because 10h has a range from -1 to 1. When you add 1 and then divide by 2, you will naturally get an output that is between 0 and 1. Last but not least, we need to define our distance function, d. And for that we can use the norm that we want. Common norms are the L2 norm, or the L0 norm, or the L infinity norm. This gives us a good idea on how different these two images are. So this is a concrete example. That's what Carlini and Wagner suggest in their papers as the best objective function. On the left side we have the function with the 10h, and this is our difference function. So how different is our perturbed image from the original image x? And here they use the L2 norm. The right term is the objective function on the perturbed image, represented by this function with 10h. And in this case the objective function, you can see it here below, consists of the logits set, which are the outputs of the neural network. This objective function satisfies the constraint we talked about before, that if the output class is t, then this objective function will have a value smaller or equal to 0. The constant kappa is actually a tuning parameter that allows you to steer the confidence of this function. So if kappa is large, then the output logits for class T have to be way larger than the output logits of the other classes. So the one constant we haven't talked about here is the constant C. C steers a trade-off between the left term and the right term. So it steers the trade-off between the similarity of the perturbed image and the original versus the objective function. And the idea is that we have very similar images, and for that C should be small. But if C is too small, we will not find an adversarial example. So how do we choose C? What we can do is binary search. We start with a really small C, apply our algorithm, find the perturbation, and then check if we find an adversarial example. If we don't, we double C and repeat this process. And this is what we get from this. In this example, we tried this on the MNIST dataset. This is graphics from the paper from Carlini and Wagner. On the x-axis, we see the constant C used, ranging from 0.01 to 100. Then on the left y-axis, we see the success probability. This is evaluated on 1,000 examples from the MNIST dataset. And on the right-hand side, we have the mean adversarial example distance. So that's the left term of our objective function here. And it shows us how different are these images. We see that when we increase the constant C, that the mean adversarial example distance increases as well. And this makes sense because C steers this trade-off. The bigger C, the more weight we give to our objective function, and the less weight we give on the similarity function. In this plot, it's clear to see that for the constant C equals 1, we'll get a really high success probability, and that was very similar in all the datasets they evaluated. Now we're ready to look at the results. First of all, we're going to see how this attack compares against networks that were defended using defensive distillation. Carlini and Wagner didn't only introduce the L2 attack, but also the L0 and the L-finity attack. These are similar attacks. They're also based on objective functions, but they use a different distance metric. So instead of the L2 norm, they use the L0 or the L-infinity norm respectively. So Carlini and Wagner evaluated their approach against defensive distillation on the MNIST and the CFAR10 dataset. MNIST is a dataset where you classify digits, and CFAR10 you classify images. Both of these datasets have 10 output classes. In the previous work from Papernot et al. About defensive distillation, they made the statement that the larger T, the better the network, or the more robust the network is against adversarial attacks. So let's see if this works for our case as well, for our attack. In this plot, we see on the x-axis the distillation temperature, on the y-axis the mean adversarial distance. And there is absolutely no correlation here between the distillation temperature and the mean adversarial distance. Even for a large distillation temperature, the distance doesn't change. The correlation is actually even slightly negative. So defensive distillation does not help against our new attack. It might help against the weak attacks that were proposed previously and that they evaluated on in the Papernot paper, but for our new attack, it doesn't help. So let's see how our approach, the Carlini and Wagner approach, compares against previous attacks, namely JSMA, Deepful, and Fast Gradient Sine method. JSMA is an algorithm that identifies the pixels that have a large impact on the output class and tries to change them. It's an L0 attack. Then Deepful is an L2 attack that is based on the assumption that the neural network is linear. Then you can iteratively solve an optimization problem that helps you perturb the image in the way to find adversarial examples. For the fast gradient sign method, that's actually the approach that we saw with the Panda. You compute the gradients and take the sign of them, and then do gradient ascent or descent towards the desired target class. And for these attacks, they evaluated on the two datasets from before, but additionally also on the ImageNet dataset. ImageNet dataset is pretty big. It has pretty big pictures as well compared to the others. And this is also very interesting to see afterwards, because some of the old attacks don't work on ImageNet because it's just simply too big. Let's see the result. These are the attacks from comparing L0, L2, and L-finity norm. The pink bar is the one from Carlini, and we can see that in all cases the Carlini attack yields a mean adversarial distance that is smaller than for the other attacks. So what does this mean? It means that we succeeded in 100% of all cases, also for the other attacks, but the mean adversarial distance, so the dissimilarity between the input X and the perturbed image, is smaller than for the others. Basically, this means that the Carlini approach is more efficient at finding adversarial examples. These are the results on the MNIST dataset. We get similar results on CFAR10. What we can see here is that the iterative version of the fast gradient sign method on the right, that this method is even a bit better in finding closer examples. What we don't have here are error bars because the authors didn't report them in the paper, but it would be interesting to see how these error bars actually compare, if they're overlapping or not. And the results on the ImageNet dataset, we see that for the JSMA algorithms, there were actually two, one JSMA-F applied on the softmax output and JSMA-Z applied on the logits. They both didn't work because it's computationally too intensive to compute that on large images from the ImageNet dataset. And for the L2 attack, Carlini performed way better. It didn't really for the L-infinity attack, but again here we don't have error bars, so we don't know what was the variance within these estimates. Each of these bars was actually computed by taking the first 1,000 images from these datasets and then trying the attacks on them. In the case of ImageNet, they sampled 100 random target classes to make it a bit more efficient. If you're interested in the details about the evaluation, check out the paper. So let's take a critical standpoint and think about this paper. Carlini and Wagner, they demonstrate an upper bound in robustness. This doesn't give us any guarantee, or not even an understanding of a guarantee, on how good this robustness is of the network. So we know when can we break the network, but we don't know when it actually works. So it is not very useful for neural network verification, but it's useful for breaking defended networks. Third point here is that the authors didn't evaluate the objective functions very thoroughly. For example, they introduced this objective function f1, where you use the negative loss, cross entropy loss, on the perturbed image, and then you add 1. And we said before that the requirement for this objective function is that the class is t, if and only if the objective function, in this case f1, yields a value smaller or equal than 0. But for this case, it is possible to find a combination of outputs that doesn't output a value smaller than 0, that outputs a value greater than 0 and still yields class t. And the second thing here is that they suggested 7 objective functions, tried all of them, and then reported the results on the best ones. And this is also, in my opinion, a little bit critical, because you can't just try a lot of things and then report the best thing that worked, because it's a way to inflate your type 1 error rate. Let's get to the summary and take-home message. We asked the question how we should evaluate the effectiveness of defenses against adversarial attacks. In this paper, Carlini and Wagner, they suggest that we use a strong attack to prove these upper bounds on robustness, and if we need a strong attack, they suggest this L2 attack as a benchmark. So in future defense attempts, if you want to break a network, why don't you just try this L2 attack and see if it's able to break your defense. Thank you very much for listening. If you have any questions, contact me. I will put the description below.